Hello everyone. So this side Manish from Skillable India. In today's session of geometric dimensioning and tolerancing, we are going to discuss the second geometric tolerance under form control, which is flatness. Okay. So why flatness tolerance is important? Step by step, how we can calculate how we can give the flatness tolerance to a feature or a feature of size. One by one, we will see. Okay. So first of all, we will understand the definition. Uh, okay, flatness tolerance. Many application needs parts with a flat surface. Okay, in case of designing molds, okay, or we are designing a press tools. So for that, many a times we require flat surfaces. Okay, so what we use in for the flat surfaces, we use the grinding wheel to flatten out the surface. Okay, so flatness is the most important thing which we required in a designing also in manufacturing also. Okay, so no surface is perfectly flat. Whatever we can do, we are doing it with the machining. Okay, but it is very uh, I will say it is very tough to get the perfectly flat surface. Okay, but using GD&T, we can develop we can develop parts with a surface that is flat enough for the application. Okay, so here it is important that the parts should be enough flat that what we are ensuring for the application, it is perfectly workable. Okay, so that's why we need to ensure that the flatness should be within the tolerance zone. Okay, the flatness call out controls the uniformity of a surface or a median plane. Okay, so here we are talking about median plane. This word is very important in flatness. With the help of 3D overview, I will tell you how these median planes are important. Okay, median planes are as needed. It defines two parallel planes. It defines two parallel planes on either side of the flat surface as the tolerance zone or for the surface. All the points of the specified surface must lie between these two planes for part approval. Okay, so in case, let's say, in this is the example. So first of all, flatness can be applied to a feature, and flatness also can be applied to a feature of size. Okay, so in this case, you can see that flatness applied to a feature which is a surface. Okay, whenever it is same as straightness, as I have already told you, that whenever arrow line, this leader line is pointing towards the surface, that means we are providing tolerance to a feature. Okay, and whenever the leader line is parallel, or the I will say in line with the dimension line, okay, like this, means we are providing tolerance to a feature of size, FOS. Okay, in this case we are providing to a feature. So two ways we can provide the tolerance zone. Okay, so so here we have an example. In this example, you can see this is the example. So this is the example of a feature. Okay, with part is having dimension of 10 plus minus 0.5. So here the dimension is provided 10 plus minus 0.5 mm. Okay, since I haven't applied the geometric tolerances till now, okay, rule 1 is applied. Okay, first of all, the rule 1 will be applied automatically. So after manufacturing the part, let's say after manufacturing this part, what we can end up like, let's say, this type of surface we can have. Okay, so end up the part like this, the peak and the valley. Okay, so this is the peak. At the top of the part will be the peak, and the bottom, this is the valley. Okay, so the difference is the flatness error. Okay, so whatever this distance will be the, in our case we have provided 0.2 flatness, or say 0.5 mm. Okay, 0 plus minus 0.5 mm is the provided. So 1 mm, very coarse tolerance I have taken over here. So 1 mm will be the maximum this can happen. Okay, maximum this can happen whenever we are manufacturing. Okay, because we are taking plus minus 0.5, so 9.5 and 10.5. So upper limit will be the 10.5 and lower limit will be the 9.5. Okay. So total tolerance zone we have over here is 1 mm. Okay. So if you refine the flat surface, let's say if we are manufacturing this part, so what will happen? So what will happen if I will remove this? So after manufacturing, we should be getting out from the rule 1. Okay. Then we have to apply the flatness tolerance. Similar, it is similar to the straightness only. But what is different is this is a 3-dimensional surface. Okay. So when we apply it to this surface or a center plane, okay, so if I will give you an example of this, if I will give you an example with this, okay, so you can see this is a part, okay, and we required flatness for this surface of this part, okay. So what we will do over here is, first of all, we will select the tolerance zone, okay. So tolerance zone, here we have the median planes, okay. So if I will just to showcase you, these are the median planes, okay. So these median planes are the whole onto the whole surface, okay. So this is the difference, this can be the difference between which is 10.5 and 9.5, which is 9.5 is this plane and 10.5 this plane, okay. So we want flatness to be within this tolerance zone, okay. So whenever we provide the tolerance, in this case, whenever we provide tolerance to the whole planar surface, what we look like, what is this looking like, the part can be okay. So first of all, okay, so part can be like this. Part surface can be like this. Okay, so the peaks and valley in this part should not be more than 0.2 mm because the geometric tolerance we have applied is 0.2 mm. Okay, so although we have the dimensional of 1 mm, but still when we provided the geometric tolerance value, it is the 0.2 mm. Okay, so it is within 1 mm. Okay, within 10.5 will be the upper limit and 9.5. But the point is that the tolerance zone, the peaks and valley of this surface will not be more than 0.2 mm. It is within this, but anywhere between this, but it is not, the peaks and value not be more than 0.2 mm. Okay. It can be like this also. And one more case can be occurred. Okay. In the next profile. So here we are applying the flatness applied to a feature. Okay. This is what we are understanding in the previous slide. So in this case also, this is the case which we have understand over here. The peaks and valley is no, should be not more than 0.2 mm. Okay. So this profile like this should be within the 0.2 mm. Okay. It can have in range of 10.5 and 9.5. Okay. So this is very, very important. While straightness has two parallel lines, in the straightness tolerance, it is two parallel lines because it is a two-dimensional entity, tolerance zone. In this case, the flatness tolerance zone is formed as a two parallel planes because this is 3D equivalent surface. Okay. The flatness tolerance zone is the volume between the two parallel planes, which I have already told you in the 3D view. Okay. So the distance between the parallel planes is the stated flatness. Okay. So whatever the two parallel planes, so between that, we are getting the flatness control tolerance value. The surface being controlled must lie within the volume defined by the tolerance zone. Okay. So one condition is this. The other condition can be this. Okay. So in this case, you can see that 10.5 mm is this and 9.5 mm part this. It can be taper. The flatness can be in taper, but still this peaks and valleys, these peaks and valleys are not be more than 0.2 mm. Okay. So the distance between the peak and valley will always be 0.2 mm. Although this, if I will take this, this point and this point, this range is 1 mm. Okay, this range is 1 mm because 10.5 minus 9.5 upper limit minus lower limit is 1 mm. But still the peaks and valley should not be crossing the tolerance value of 0.2 mm. Okay, so peaks and valley are defined. Okay, although this is into the taper, it is acceptable, but the peaks and valley should not be more than 0.2 mm in this flatness tolerance. Okay, so this is the condition 2. So this is the second condition. Okay, now we will understand that when flatness applied to a feature of size. Whenever flatness applied to a feature of size, flatness on a derived median plane, DMP. Okay, so derived median plane, this word is very important, which I have already shown you in the 3D view. Flatness on a DMP is another way of using flatness in GD&T. In this case, the flatness symbol is applied to a feature of size. Okay, so in this case, you can see that we are applying this flatness symbol to a feature of size rather than a surface. The control feature is the virtual DMP of the reference feature of size. Okay, this has many practical applications. Most notably is the stacked components. Okay, so we are talking about the stacked components in which two components are stacked with one another. Okay, another point to bear in mind when using the flatness symbol of a derived median plane DMP is that the maximum material condition MMC and the least material condition LMC modifiers are also applicable to it. Okay, so the flatness call out in the figure below condition contains the MMC modifier symbol. Okay, so in this case you will see that whenever we are providing tolerance to a feature of size, okay, so we can have the maximum material condition modifier or the least material condition modifier. So in this case we are providing flatness to the feature of size. So you can see that the flatness symbol is applied to a modifier is given to the tolerance zone. Okay, so this is very important. Now in this now we will see where are the center planes. Okay, so why these center planes are important in this case. So let's say if we are taking a profile and the so here what we have is, this means that after manufacturing we can end up with a part like this also. Okay, let's say this can be the condition where the part we manufactured like this. Okay, so the center plane, if I make one center plane, so the center plane will be also tilted. Okay, so center plane of the part will also be in a round shape. Okay, now if you take the total tolerance between the two parallel planes, so here I am making two parallel planes. Okay, so in between this is the median plane between this. So these are the two parallel planes and the center plane of the actual part. So this dashed line is the actual center plane of the part. Okay, which is within this two planes, which should not be more than 0.2 mm. Okay, so this is the case. This is the how we can control. This is the controlling of the flatness of for the center plane. Okay, if the part is manufactured with the round profile. So this was added. This manufacturing or the maximum material and the minimum material condition. This was added in the 2009 standards onwards. Okay, since we are applying flatness to a feature of size only, here we can have maximum material condition. Okay, so whenever we are applying maximum material condition, we are getting more tolerance. Okay, so when the part is manufactured at 10.5, so we have the tolerance of 0.2 mm. As we move from MMC towards LMC, okay, at 9.5, so we have the more tolerance zone, which is 1.2 mm. Okay, so as we move towards MMC from LMC, we will have more tolerance zone than we have at MMC. Okay, so the part is produced at 10.5 mm is having the tolerance zone of 0.2 mm, then the flatness error will be in this case, okay, will become 1.2 mm at LMC condition. Okay, for the planar surface, this is the feature of size. When we apply the condition to a feature of size, we get more and more tolerance. Okay, so this is, although that's only the thing which we have already discussed, that flatness on a derived median plane DMP for a width type feature of size. Okay, so in this we are talking about two surfaces, this surface and this surface. Okay, so we are controlling two surfaces. So the derived median plane into the engineering drawing is planar, but after manufacturing this part can be tilted, okay, which I have already told you. So as per the rule 1, automatically limits the flatness deviation of the each surface. Thus, to have any meaning, a separate flatness tolerance applied to either single surface must be less than the total size tolerance. The flatness surface tolerance feature control frame associated with the width dimension replaces the rule 1 dimensions or requirement for perfectly formed at MMC, with the separate tolerance controlling the overall flatness of the width type feature. Okay. So in this case, we are controlling the width type feature. So with this, the median planes, this is called the median plane. Okay. Now, how to measure the flatness? If you want to measure the flatness, what we have to do is place the target. Okay, so whatever the target is, let's say this is the part. Place the target in the precision table. This is the precision table over here, plane table, and secure it in place. Set the dial gauge. So in this case, this is the dial gauge indicator. Okay, so that its measuring part comes into contact with the measurement surface. So this part over here is coming into the contact with the measurement surface. Okay, move the target. So this target will be moved here and there. This part will be moved here and there. So the target, so that the measurement surface is evenly measured, and read the dial gauge value. Okay, so this dial gauge indicator will tell that how smooth the surface is. Okay, if the variation is large, it will rotate like this in the 360 degree. Okay, so the largest deviation value is the flatness. Okay, so the largest deviation, whatever the deviation will be in the dial indicator, it will measure the flatness. What will be the disadvantage? So the measured value may change depending on any change in the measurement point. Since the measurement point change depending on how you move the target, therefore it is difficult to obtain a stable measured value. Okay, so dial indicator moves and records the flatness error. Okay, so this is very important because in this dial indicator, if I will say, so in this dial indicator, it will record the flatness error. Whatever the flatness error will be recorded in this dial indicator. Okay. Now one more method is there to how to calculate the flatness. So if we will discuss, so how to measure the flatness, we have the using the coordinate measuring machine or the CMM machine. So CMM machine is very important machine which we regularly use for measuring the flatness, profile measurement. Okay, any surface component to check it is right or wrong. Okay, to inspect the part, we use this machine a lot. Okay, so CMM, what is CMM? If I will briefly tell you, so CMM is a coordinate measuring machine. It has one probe. With the help of that probe, we collect the point cloud data. Okay, so with the help of these are probes. Okay, so you can see these probes over here. This is a single machine probe. This is the probe. With the help of this probe, we collect point cloud data. And with comparison of multiple points. Okay, let's say uh, this is the part. So here we will check. Here we will check. So at multiple points, we will check the part. and whatever the variation will be. Okay, so let's say whatever the variation in the part, whatever we collect into the point cloud data, whatever the variation into the part, it will collect into the computer. Okay, so with the help of CMM, we are collecting the point cloud data and it will be recorded. So whatever will be the deviation, let's say this deviation will be checked, whatever tolerance we will give. Let's say if I have given 0.5 mm, okay, so that will be recorded and that will be given. If it is inside the tolerance zone, let's say this part is inside the tolerance zone, so it will be given that this part is approved. Okay, so this part is approved if it is within the tolerance zone. Okay, if it is outside the tolerance zone, this part gets rejected. Okay, so this is how we calculate or to measure the flatness with the help of coordinate measuring machine. Okay, so this is all about flatness. In the next discussion of geometric dimensioning and tolerancing, we will discuss the next geometric tolerance zone, which is circularity. Thank you. Thanks a lot.